My name is Ashish Ippili. I'm part of the professional services team within Google Cloud, and I'm based out of India. Today, we're going to learn about how to build a great messaging application that can deliver over billion plus messages a day. And also, see how GCP is probably the best place to build this. Right. I've joined Google Cloud about 2 years ago. And before joining Google Cloud, I've been working with a number of enterprises, helping them leverage technologies around collaboration and messaging. So when I joined Google Cloud, obviously, I was very keen to understand how Google does messaging and how its customers do this. So when I looked around, I realized that there are a number of customers who use Google Cloud to deliver messages to their customers. And we ourselves, as Google ourselves as well, has a number of applications which does messaging. Snapchat doesn't need much of an introduction here, I hope. Hike is a popular messaging application in India with over 100 million registered users. BBM is still very popular in Indonesia, if you're not aware of it. So they have about 60 million monthly active users. ShareChat is a custom-made or a tailored platform for vernacular languages in India, very popular in Tier 1 and Tier 2 cities. And then internally as well, we have Hangouts, Allo, Chat, and Talk, and a number of applications. All of these actually leverage the technologies on Google Cloud and deliver the infrastructure stack. So there's one striking difference in the applications that I used to work earlier and these. And it's the sheer scale at which these operate. The organizations which I used to work earlier had tens and thousands of people. Comparatively, all of these have millions of users delivering billions of messages. So it was fascinating for me to understand how the technologies around this are actually framed or put together to ensure that we deliver messages to the customers appropriately. So today, I'm very excited to share the story of how this is done. Fortunately for me, I've had the opportunity to work with a very talented team at Hike who have decided to move to Google Cloud about 10 months ago. So it is in this journey, when we migrated them to Google Cloud, I've learned a lot about how a messaging application works. So let's dig a little deeper and see the building blocks of a great messaging application. First and foremost, you would obviously need an infinitely and instantly scalable load balancer to take the traffic from millions of users which connect to your application. And then you have to connect the users to the backend systems. So you need a mechanism or a system to manage these connections efficiently. And that's where the connection handling comes into the place. And then you need to be able to authenticate the users you're connecting to you and be able to deliver these messages securely and consistently. And obviously, with the so many billions of messages coming through, you need a job management system which basically manages these jobs in an asynchronous fashion. And then we have a message processor. A message processor, basically what it does is it takes a message and understands what needs to be done with that message. The action that you need to take for a single one-to-one chat or a group chat, or for example, when a user is online or a user is offline, the action that it has to take is different. So the message processor is the one which decides what needs to be done around a message. And obviously, you need a message store. Think of it as a place or a database where you store all these billions of messages and be able to retrieve these messages very quickly when you need them. So you need a database which can do this for you. And then you need a file store or an object store to save all those cute cat videos, the memes that you share, and the selfies that you share with your friends. So all these object files go and get stored in the file storage as such. And then notification management. This is very key. So the notification management system, what it basically does, it identifies whether your user is online or is he offline. And if he's offline, send him a message saying, hey, you got a message. and bring him back to the application to check his messages. So all this is dealt by the notification management system. Now, last but not the least, you need a great analytics platform behind this to take data-driven decisions and be able to be agile in terms of decisions to ensure the startup works really well. So to see, now that you know all the basic building blocks here, we're going to see how these things are put together. To help you explain that, I'm going to invite Aditya, Director Engineering at Hike. Aditya?
Thanks, Ashish. Hello, everyone. I am Aditya Gupta, Director Engineering Hike Messenger. Today, I'll walk you through the journey of Hike Messenger. Hike is one of the popular messaging apps in India, started its journey in year 2012 when mobile internet connectivity was not that great and smartphones revolution had just started gaining popularity with aim to connect people together. At present, we have over 100 million plus registered users exchanging over 40 billion plus messages over a month. So how Hike is different from other messaging apps? Hike at present is situated at the intersection of social and content space. It not only provides its users a platform to chat without compromising on privacy, but also provides a bite-sized snackable content in the form of news, cricket, jokes, and much more. Hike is more popular among youngsters in the age bracket of 15 to 24 because of its features like hidden mode, stickers, timeline, and stories. Hidden mode allows you to hide your selected chats with the rest of the world, which is a big thing in India, especially with a lot of users, especially with school kids, who share their parents' mobile phone to connect with their friends. Sticker Shop, Sticker Shop offers you over 20,000 stickers in 40 different languages, which is a great way to share your feelings with your friends without uttering a word. Features like Timeline offer special memories and Hike News in over 8 different languages is a great way to remain up to date. Now, I'll walk you through the basic messaging architecture at Hike. Also, we'll be discussing few key components of our infrastructure and how Google is helping us to manage it better. Sure, let's start. So, Hike messaging runs on MQTT protocol over a persistent TCP connection between client and a server. On a given day at peak, tens of millions of connections, clients connect to our MQTT servers. So for that, you require a good load balancer in the front layer, which was served by HA proxy in our case. Yeah. So to connect to HA proxy layer, we have a DNS mqtt.am.hike.in, which further divides into 5 different CNAMEs, AMQTT to EMQTT respectively. Each of the CNAME further resolves to cluster of HA proxy IP addresses. Along with this, we used to maintain a list of public static IP addresses which were hard-coded in clients because if DNS resolution fails, which used to happen because of poor connectivity of faulty ISPs. HA proxy in turn forwards the connection to MQTT server and also do SSL termination. At the start of every connection, client sends a connect packet with UID and password for authentication. Connection gets established only after successful authentication. So for that, you require a auth service. After that, whatever messages client sends, we used to encode them into different queues for asynchronous processing. There are job processors which used to consume these messages from these queues and process the message sent by the client. To send the message back to the recipient, these job processors used to submit the message to message delivery service, which in turn sends or stores the message based on whether the recipient is connected to any of the MQTT box or not. So this is how basic messaging works. So where exactly Google helps us in this? For that, I would say at every layer, be it a front end, a business logic, or a backend database. While evaluating GCP, we did a small POC and found out some major advantages which prompted us to move to GCP stack. Some of the advantages are, first, Google provides uh, infinitely scalable front-end layer GLB, which can scale quickly on network or connections both. It suits perfectly to our needs, and also we found latency improvement of around 1.7x as compared to HA proxy layer. Second, superior hardware. We ran a simple test of Redis benchmark on a similar hardware machines and found throughput to be 1.7x more on the GCP hardware as compared to our previous cloud provider. Combining this fact with managed instance group, which can auto scale on CPU load or any other metrics, it provides a simpler architecture with cost benefits. Third, Google provides a lot of APIs in vision, ML, and data processing, which are a lot easier to integrate if you are on GCP stack. So this is how our architecture looks like after migrating to GCP. As you can see, we don't have to maintain a list of HAProxy machines. We don't have to maintain different C names and also a list of public static IPs. GLB just provides you one public static IP, which is behind a DNS and also hard-coded into client if DNS resolution fails. As you can see, now all the processing layer has been replaced by a managed instance group, which can scale on CPU or load. This helps us in saving a lot of cost. On the database layer, we have a lot of footprint on HBase, which we are now migrating to Bigtable. It not only provides a better throughput, but also takes away the manageability from us. So this is the final architecture, how our messaging looks like. Now I would like to invite my colleague Gaurav to deep dive into two specific components, job processors and address book database. Gaurav?
Thank you, Aditya. Hello, everyone. I'm Gaurav. I'm Director Engineering in Hike Messenger in India. And just give me 1 second. Today, I'd like to talk about a couple of things. First one is the job processors, and then it's the address book, as Aditya mentioned. So let's start with job processors. So job processors constitute an important part of any messaging application, as this is where most of the business logic resides. Now, when we started building our application, we started with a monolithic architecture where all the components were in a single deployable unit and all the processing was done synchronously. Now, this approach is usually the quickest to develop, and that's one of the main reasons why we choose to do it this way. But very soon we hit scale and we started facing the pitfalls of this approach. Now, we had frequent downtimes. We weren't able to scale independent components separately. Continuous deployment became a hassle, and the code base was so large and complex that none of the developers were able to understand it well. So then we broke the entire system down into multiple components, and the process of delivering an incoming message was made asynchronous. So this is how it looks like. This is how it looked like back then. So all the incoming messages were passed through a sharding function, which helped identify a particular queue on the basis of message type and the user ID in the message. Okay, now each of these queues had a single consumer associated with them, which picks up messages from these queues and tries to deliver them to the end users. Now, as you would know, one of the main requirements from any messaging application is an ordered delivery of messages. There can't be more than one consumer for each of the queues, or else this guarantee won't be maintained. Now, this architecture helped us in separation of components, each of which could now be independently scaled up or down as and when required. It was much better scalable than the previous monolithic system that we had. However, this system was still a bit difficult to scale up, as we were limited by the maximum number of consumers, which always had to be equal to the number of queues in the system. In other words, in order to scale the system, we needed to increase the number of consumers, and to increase the number of consumers, number of queues had to be increased, which in turn required a change in producers so that the newly added queues are taken into account by the hatching function that you see up there. Now, another major issue that we faced with this approach was that of starvation. So messages that get queued in the end are always delivered in the end as well. So the older messages get delivered first. Now, since these queues are shared by multiple users, it may so happen that a user's messages end up in a queue which is already full of messages, and the user experience for that user won't be great because that person would have to wait for much longer as compared to other users. So we re-architected the whole solution and moved to something that we internally call as per user job queue. This is how it looks like. So again, all the incoming messages go through a function, and a queue is decided only on the basis of message type in this case. And so the producer's job is only to put it into an appropriate queue on the basis of message type. From there, these messages are picked up and placed into one of the user queues, depending on which user it has to be delivered to. Now, the limitation still exists that in order to deliver the messages in the order in which they were received, we can still have only a single consumer per queue. But since each user has its own independent queue, scaling this architecture up only requires us to increase the number of consumers, which can be easily put on auto scale. Now, this architecture in particular helped us scale to more than 1 billion messages a day, and we hope that it would continue to scale up as and when we get more scale. So let's move on to the other one, other object, which is the address book. Sorry, I'm getting a bit confused on this. So address book is one of the biggest data stores in Hike and has undergone a lot of transformations over the years. The use case for address book is very simple. Whenever a user joins Hike, the entire contact book of the user is synced back to our servers. And this information is later used to serve out different use cases. The read pattern of this data is actually two-dimensional. First one is a forward-looking query, wherein you want to query all the users that are there in a particular person's contact book. And the other is a reverse relation, wherein you want all the users who have this particular user in their address book. Now, when we started building this messaging app, NoSQLs were very popular. That was the buzzword, and MongoDB was one of the most popular one back in those days. So we also decided to build our address book using MongoDB. Now, back in those days, MongoDB was on its MAP v1 engine, which used to acquire database level locks. So initially, the way we architected the system was we had one Mongo database for forward-looking relations and one database for reverse relations. However, since the use case was very write-heavy, we frequently hit scale issues with MongoDB because of its DB level locks. So as an immediate remedy, what we decided to do was we sharded the Mongo cluster into multiple instances. That helped for a while, but the rate at which we were growing back then, we knew that we had to do something completely different. Now, if you look at the data structure of address book, it's the schema is pretty fixed. You have user A, whose address book we've picked up. There is user B in the address book, and there is a name and maybe some other metadata. So since the schema was fixed, we decided to move the entire load to the traditional RDBMS. We chose MySQL for that. And we moved to MySQL. Now, MySQL served very well for us for multiple years. As and when we required more capacity, we used to scale up the machine. We were able to vertically scale our machines up to about 3 billion rows in a single table. And basically, the table looked like there was a user A, there is user B, and then there is a column for metadata. Now, since we required the read patterns on both user A and B, we simply made indexes on both of them. At one point, since we were vertically scaling this up, we ended up with a machine with 104 gigabytes of RAM, and that was the max that our service provider could provide at that point. So going forward, since we were still growing, we had two options. We could either shard our MySQL workload into multiple instances, or we could have moved to a database which provided sharding by default. So we chose the latter, and we moved on to HBase. So when we started migrating to HBase, the initial design that we chose was a white schema, wherein the user ID, whose address book we've picked up, the user ID became the row key, and all the contacts became different columns in the same row. Now, since a user's address book can have as little as maybe 10 or 15 contacts, and it can go as big as tens of thousands of contacts, with very frequent deletions and very frequent updates, HBase cluster was going through very frequent major compactions, which wasn't desirable at all. So we knew we had to change something again. What we did with the HBase cluster was, instead of a wide schema, we moved it to a tall schema. wherein the combination of user ID A and user ID B became the row key, and the metadata was the only thing that was left for columns. This architecture served really well for us. It's horizontally scalable. We haven't really felt any need to replace that. But when we moved on to GCP back in late 2017, we evaluated Bigtable and realized that the throughput in Bigtable was about 1.5 to 1.7 times faster than the HPace, the throughput that we were getting in HPace. So we decided to migrate everything onto Bigtable. One reason to move that was latencies, and another reason was it takes away all the manageability effort from us. Basically, Google does everything under the hood. So earlier on HBase, whenever a machine used to go down, a data node used to go down due to hardware failure or whatever other reason, we used to see spikes in latencies. But ever since migrating onto Bigtable, we haven't really seen any such spikes. So Bigtable is serving really well for us, and we hope that it continues to serve the same way. So that's all I had for the address book journey. Sorry. What's next? We're actually doing multiple POCs for migrating use cases onto some of the managed services that Google provides. Some of the ones we are evaluating include Spanner and Bigtable. So we hope to move very soon onto those. Then we're also evaluating Kubernetes and trying to integrate Spinnaker for continuous delivery of our code bases. Now, with that, I'd like to call on stage Suchit from Google, who would talk about the basic building blocks of the analytics pipeline.
Hello. Yeah. Thanks a lot, Gaurav. So let's talk about data and analytics, right? So when you're managing hundreds of millions of users, having a solid and stable data analytics pipeline becomes really important because you're always running A/B test, you're always collecting a lot of events, and you want to process them and take data-driven decisions as quickly as possible. So this is how a typical data analytics pipeline, a streaming one, could look. On the left-hand side of the screen, you can see that you have all your sources, right? So you have your analytics events, you have all your logs, you have some external data sources coming in, and then you have your transactional databases. All of them can be put in a messaging queue if you are building a streaming pipeline, or you can just do a batch processing as well. And then after that, you need to have an ETL processing mechanism to transform that data and finally dump all of that into a data warehouse. And once your data is in data warehouse, you can start building dashboards for all your internal teams, start your business analysts start working on your business intelligence, start getting more insights out of that data. And then your machine learning folks as soon as they see the data, they'll start building models, start working on them. Let's see how this data analytics pipeline maps to GCP, right? And this is one of the ways you can build a data analytics pipeline, a streaming one onto GCP. Right, so you have your analytics events, which you can directly push into a messaging queue. Logs you can just store your logs into the GCS, which is the cloud storage. External sources you can sync again GCS with your put in your external data, third-party data onto cloud storage. And then you have databases. You have a lot of choices around Spanner or MySQL, Postgres, or managed SQL databases. For messaging queue, we have our scalable cloud PubSub. We use it internally for a lot of use cases, and it can scale to very, very high ingestion speeds. Then we have our managed Hadoop offering, which is the cloud data proc, in case you want to build a batch pipeline and start directly processing your logs there. Once your data is inside PubSub, you can build a cloud Dataflow pipeline, which is just an Apache Beam runner onto GCP. So it's again open source. It's a managed runner, and it scales automatically. You can just define the set of nodes, and it will scale up and scale down based on how quickly and how much money you have to process that, the money you're willing to spend on that. And then very recently, I think yesterday we announced Cloud Composer, which is our managed Apache Airflow. You can use Airflow to control and schedule your DAGs, which are your data pipelines. When do you want to run them and how do you want to organize them together? And then there are other ways also, like you can directly import your Spanner. We've recently announced Spanner backups, and you can import them into BigQuery as well. So that again directly goes to your data warehouse. Now Apache Beam, using Apache Beam, you can dump all of that data into BigQuery. You can either stream or batch upload it into BigQuery. Then for managing dashboards, we have our Data Studio, which can directly connect to BigQuery, and then it can help you build your internal dashboard, which you can expose to your teams. For business intelligence, we have managed Jupyter Notebooks environment. We have a Cloud Data Lab. We also have Kaggle, wherein you can, if you want to try out third-party data, build some interesting insights onto that, you can use that. And then finally, we have the Cloud Machine Learning Engine, which lets you train your machine learning models at scale, serverless, fully managed. So you can easily read data from BigQuery, and it will automatically scale out, scale up, scale down, based on your needs. So all of this end-to-end is completely managed. There are a lot of components, but usually I think with PubSub, Dataflow, and BigQuery, it is quite straightforward and easy, and it's good connectivity. So now, let's see how was Hike's journey, right? So when you're migrating and building your data pipeline, and you're coming in from a different environment, be it on-prem or a different cloud provider, it is not always so straightforward. There are their own challenges, and you have your own experiences. So I would like to call in Manjeet to talk about their journey around how did they manage to process around 2 petabyte of data as quickly as possible onto GCP.
Thank you, Suchit. My name is Manjeet Singh, and I'm leading data infra team at Hike Messenger. And today I'll be discussing about the journey of data pipeline at Hike Messenger, and also how Google technologies like Dataproc, Dataflow, GCS, BigQuery benefited us. Hike is a very data-driven company where every decision is taken based on data. So if you talk of data, on an average, on daily basis, we are generating approximately 14 to 15 billions of row, which is coming around 4 to 5 TB of data. And in all, we have accumulated more than 2 petabytes of data. Now, let's move to the slide where we can have the look at the older data pipeline. So this is how it looks like. As Aditya explained, we have different kind of servers like HTTP servers, MQTT server, analytics servers, and we have the clients which are talking to these servers, and clients generating their own analytics logs, which are going to analytics servers, and we were saving into the log files. Then other servers like HTTP and MQTT servers, they were generating their own analytic logs, and it was going into log files. Then we had the cron tab set up on each and every machine, which were copying hourly data into the cloud storage. Then further, we had the cron tab jobs, which are copying data from the cloud storage to our in-house Hadoop cluster. So for batching, we were using Hive. We were using Hive, and it was running on our own in-house Hadoop cluster. And all the aggregated tables were going into the columnar database for the faster data access. And Looker was our BI tool, which we were using. And Hue was the ad hoc analysis tool, which we were using. But with this pipeline, we were facing many challenges. So let's have a look at the challenges we were facing. So we need to set up analytics cron on every machine whenever we add a new machine. And there was a loss of logs in case of machine failures. And replaying of missed files was very messy stuff. And in the older data pipeline, we were processing data at hourly level. So it was not as real time as we were expecting. And as we had the in-house Hadoop cluster, so we were managing it manually. It was not an easy job, and it was a always running cluster, so there was a huge cost associated with it. And once we migrated to GCP, so we improved upon our existing older data pipeline by adopting various Google technologies and other technologies. So let's have a look at the existing data pipeline we have at Hike Messenger. So this is how it looks like. So now instead of generating data into log files, we are generating data into Kafka. And then further, we have the in-house Kafka consumers, which are consuming data from Kafka. And then we are cleaning and denormalizing and then generating the ORC files. And at every 15 minutes, we are copying these ORC files into Google Cloud Storage. And then we have the Hive, and we are using Hive for batching. And Hive is running on Dataproc. And in Dataproc, as Dataproc is managed by Google itself, so in Dataproc, we are using two kind of machine instances. Like one is the fixed worker, another one is the preemptible ones. These are the auto scales. We have set up the min and max limit, and which get scale out and scale in based on our settings. And all the summarized tables we are pushing into Google BigQuery. It is going through Google PubSub. And then we have the machine learning and DS algorithm, which are running on our Hive cluster and Google BigQuery. And then we have the Tableau as the BI tool, which is talking to Google BigQuery. And then we got many advantages after moving to this pipeline. So let's have a look. Now, after moving to this existing pipeline, we need not to set up any analytics crons for copying data from the servers to the cloud storage. And then fetching data from Google BigQuery becomes super fast. It is more than 10x faster. And now we are processing data at 15-minute level. So we are moving towards very near real-time analysis. And now we don't have any in-house cluster, which is we are using for data processing. Now, as we are using Google Dataproc, so it is managed by Google, and we are using it in a auto-scaling manner using the preemptible MIGs. And then we have the Kafka, and we can use the Kafka for building many data-driven services. And well, we are still improving upon our existing data pipeline. And sorry. So this is how our future pipeline we will be having. And in future, what we are trying to do is, instead of having in-house Kafka consumers, we are using Dataflow. And Dataflow will be consuming data from the Kafka. And then what we are trying to do is, this will be a metric-driven pipeline. We are using a rule engine for generating the matrix in the Dataflow itself, in the transform phase of the Dataflow. And then we are aggregating and generating the second level of matrix, and again aggregating. And then final, we are pushing into Google Bigtable and Google BigQuery. And Google in Bigtable, we are putting some data which is being used by our application for real-time access. And then BigQuery will be our final data warehouse, where our machine learning stuff and Jupyter notebooks and Tableau will be using it. And this is all about our journey. And thank you very much.